All right. Yeah, so the first problem, I know you don't have the problems just yet, so I'll just write it here. So the first problem is find all the quadratic sub-extensions.
We have problems in the example.
You do? All right, good. Okay, yes. So yes, so we need to find the quadratic sub-extensions in Q extended by the 24th primitive root of unity. How would we do that? Any ideas?
So we and from each numbers we can take square roots, or maybe it's about discriminants.
So from which numbers can we take square roots in this case?
I think that it will be divisors of. No. Not divisors of 24.
Divisors of 24. Is that right?
It's wrong. So, for example, can we take a square root of 2?
Square root of 2.
Can we express it to as linear combinations of roots of unity? Yes.
And how would we check that?
There is like Z3 which has square root of 2 itself.
Okay.
Like root of unity of third power.
So for example, yes, so later 3. Oops. Yes, so what's theta 3?
It's 1 plus I. Сейчас square roots of 3 там, наверное, divided by 2.
Well, so let's see. So
we need to draw a picture.
Yes. I can share. Hold on. I can let you write on the board.
No.
Hold on.
If we want to take a square root of 2, we need to consider the 8th root of unity. It's obvious from picture.
All right. So you want to write it down? Okay.
I can try, but I need just a minute to take my mouse.
Me. Hold on.
Okay, so I can try. So we have a circle and it's divided like 2.
That's right. Yes.
This is 8th root of unity. And we know that it has a coordinate like this thing 8. How to write that? Okay. Так, как-то оно все странно работает. So this is like so we can take this, we can take like to the power of 7 will be the same thing with minus
Mm-hmm.
And if we like, and if we sum, it will be square root of 2.
Okay. Can we get any other extensions?
We can get
Sorry, I can't hear you. Where'd you go? Can anybody say something, because I wonder what's happening? Ah, okay, good. Uh-huh. So what other ones can we get?
we can get this from here.
Mm-hmm. And by taking what?
By taking sum of like this and this.
Mm-hmm. Mm-hmm. What other
For
ones?
example. We can multiply this and get a square root of 6. And it will be quadratic extension 2.
Uh-huh. How about any imaginary maybe extension? What do you think?
Imaginary extensions. So the question is,
Oh,
do we
it was just
I?
three?
Of course, we have I inside.
Mm-hmm.
Like, yeah, it belongs here. So we have -3 and -2 and -6 sub-extensions too.
Mm-hmm. Mm-hmm. Okay.
Sorry, quadratic sub-extensions, it's sub-extensions of index 2 or
Of degree 2.
or degree 2, okay.
Yep. Mm-hmm.
What's the difference?
Well, yeah, I guess in this case there is no difference. Mm-hmm. Mm-hmm. All right. Yeah, so I guess that's it. So we have square root of 3, we have square root of 2, we have square root of 6 correspondingly.
But why? So it's all interesting divisors of 24 in terms of square root.
Can we get, in fact, can we get all of the divisors?
Yes, because like 24 factors as 2 to the 3 multiplied by 3.
Mm-hmm.
So we can get all divisors of 24. We can get square roots of all divisors of 24.
Yep. Mm-hmm.
But the question is why we can't take other sub-extension.
Well, suppose that we have a difference of extension, then what then you can, yeah, then you should be able to express yes, then you should be able to express that sub-extension as a sum of roots of unity, right? Or as a linear combination of roots of unity.
Square root as a Z linear combination of, or Q linear combinations of roots of unity.
Mm-hmm. Mm-hmm. And what is the problem with that?
I think there
What
should
do
be
we-
problems with discriminants, but I don't understand discriminants well. But maybe it should divide something. Or
Sorry, what's the conjecture for now?
For now, it's just that the quadratic extensions are the quadratic extensions by the square roots of the divisors of 24. Mm-hmm.
So, for example, square root of 7 can't be expressed via these things. like roots of unity of 24.
You're saying it cannot be?
I claim that it cannot be, but and I feel it, but I can't prove it yet.
Well, so suppose.
Do we know that all quadratic sub-extensions are, so we need to find a subgroup of z over 24 z star of index 2 and to look at the sub-extension that is that does not change under the
Yes, that's a good idea.
Oh, yeah, because everything is goes, yeah.
Mhm. So how? So what is the multiplicative? What is the Galois group of z over 24? I mean of z to 24. Yes, it's this. And what is this? Hold on, it's this. So what is this? Can anybody tell me?
it should be I think it should be z over 2z multiplied by z over 4z.
Would you say z over 2z multiplied by what?
Z over 4z.
Let's see. Does that have the right number of elements? So what is phi of 24?
It's 8, yes.
It's 8. Okay. Yes. All right. Sounds right. And then
Sorry, but maybe it's wrong. Maybe it's z over 2z in the power 3. To power 3. So we have.
Yes. Well, let's check. Right.
Okay.
Does it have an element of degree 4? Oh, of order 4, I mean. Let's see, does this have an element of degree 4?
Actually, it might not have one. Yeah, I think it does not, because like 5, 7, and 11 neither qualify. And so I think it's z to that to the power 3.
Let's check real quick. So let's see. We have
Because it's z over 8z star, and we know that it doesn't have an element of degree.
Okay. So, sorry. So how many? Yes. So how many subgroups of index 2 does this have?
Well, I guess 3, so they're all is isomorphic. I don't, but like,
I think that we can take any element. So
yeah, you can take actually you have like 7, right? Because
7.
you can take any combination of the z to z group, which is not like all 3 of them.
Yeah, but we're talking of index 2, not about. Well, I mean, I guess.
Oh yeah. Oh, index. Yeah, I guess if you need index, you only can take like 2 of those groups, and the third must have a constant element, or you can actually no.
No, you can have more, right? Yeah.
You can have more.
Subgroups of index 2 is divided by 2 of its elements and contains 3 elements. So we can like count options to take 2 elements. It will be 7 multiplied by 6 divided by 2, and then divide it by 3. So it will be 7 again.
So you're saying 7, and how many divisors of 24 do we have? 1.
You mean square free divisors?
I'm yeah, yes. How many square free dividers do we have? Mhm.
2, 3, 6, and minus them.
Yep, that's right. 2, 3, 6. Plus minus. Yep.
But it's not enough. Why you're writing 1? 1 don't.
Well, because we also have negative.
Minus 1.
Yeah.
Yeah, of course.
Mhm.
And it's exactly 7.
Yep. So that's right.
But we have done this like by hands. And is it true for arbitrary number instead of 24?
Well, I'm not sure. I can tell you about P. Well, I know for P it's true. But for a prime number. But
Okay.
I'm not sure about others.
Sorry, could you explain once again why these divisors of 24 corresponds to the how they corresponds to these sub extensions?
So each we can get we can get a quadratic extension. So square roots of each of the numbers listed, they belong to this field, right? And there are 7 of them. And we also know that in the GLA group, there are 7 subgroups of index. There are 7 subgroups of index 2, right? So we know.
Okay.
We know that all of those quadratic extensions, they correspond to the GLA subgroups, to the subgroups of the GLA group of index 7, right? Of index 2, sorry, and there are 7 of those, and there are 7 divisors that we 7 square free divisors. Yes, very nice. All right, moving on. So we want to show that Q extended by zeta 7 and Q extended by zeta 20. They both have class number 1. So what do we apply here?
Excuse me, it means that every fractional ideal is rational, yeah?
Every fractional ideal is principal, yes.
It's principal.
Yes.
But we have a class number formula. Let's see if it uses here. Is it enough to prove that any rational ideal, which means just an ideal, is principal, yeah? So this is a ring of principal ideals. Oh, it's not.
Yeah. We need to prove that it is in fact a PID, yes. Principal ideal domain.
You mean that integral elements have a principal ideal domain?
Yes.
Because it's all about integral elements.
Of course. So what would we use here? Does anybody have an idea?
Well, in theory, at least for the left field, we probably could prove that you can divide an element by an other element which is not 0 and like get a remainder which has a lesser norm, but I don't know if it's good.
You can show, you're saying that you can show that it's a Euclidean domain, right?
Yeah.
That it admits a Euclidean norm. Well, I mean, is that something you can prove?
I'm sorry, is it true for any prime number? Or should we use a particular properties of number 7?
Well, you need to use, you need to use some formula. So what formula could you possibly use here? What formula is useful for calculating something about the class group, ideal class group?
But we are talking about just proof that corresponding integers ring is good. Is it maybe it's well known that it's Euclidean for any prime number?
No, I mean, that's
Or
not
not?
true, right?
That's
Mm,
not true. Okay.
It's not even a unique factorization to me, much less Euclidean.
For some prime numbers.
For some prime
Okay.
numbers, it's true, but are we gonna, are we gonna rely on something powerful like that, or is there's a formula? There is a formula that you have studied.
There is a class number formula,
Which
but
one?
it's hard enough.
Yeah,
I
exactly.
don't even remember anything from it. It's some discriminants, maybe.
But do you have, yes, but do you have a different formula? Do you have some other formula that tells you something about the ideal classes? That is simpler. There was a whole lecture on it, actually. Do you know?
I don't remember anything on these formulas, but there is actual notes, of course, but maybe you will just say it if no one else can remember.
Well, I'll tell you, it's Minkowski bound.
Minkowski bound is that any ideal has a representative of norm less than some weird expression.
That's right.
Any fractional ideal has a integral representative with norm less than some
Yeah,
thing
that's right.
that includes pi, for example.
Right. So how about you you compute the Minkowski bound for both of these numbers, and what do you get? For both of these fields, and what do you get?
Of course, I can do it.
Yeah, I mean, you can just plug it into Wolfram, right? Wolfram alpha.
Plug what? Minkowski bound? It's
Oh yeah, you have a Minkowski. You don't have a Minkowski bound in your lecture notes?
Have, but
Okay,
I
yeah.
should open it.
Okay.
And so Minkowski bound, I can write it.
Yes.
It's this, which is discriminant of the field multiplied by how to undo. I undo too much. It works not good. 4 over
Yes, it's 4 over pi to the
to
power.
To the power of this, and this thing is
The
number of complex embeddings, and
the number of complex embeddings divided by 2. Yes.
Number of pairs of complex embedding here, and there will be this to this. Where n is degree of extension.
Yep. So what is n in the first case?
N is 6.
That's right. And what is the number of complex embeddings?
It's also 6.
It's also 6. That's right.
But we should divide it by 3.
Yep, so it's 3. And what is the discriminant?
Who knows?
Well, you can compute it, right? You just need to write down the expression.
Trace form. Trace form is no. I remember that on some seminars we calculated such discriminants without trace form, and it was.
You mean at the previous seminar? Well, we used the we use the formula. We use the formula for what's called for the discriminant of the cubic polynomial, but we don't have that now. So you can just
No. On some old seminars.
You can
No,
actually
no,
compute
no.
it. You can actually compute it by using the determinant, right? You can look at the determinant of the matrix, right? Formed by the
Yeah,
constant.
matrix of trace form, I say.
So what is it?
So it will be big matrix enough. So we know that like there is basis of extension, which is all these elements.
So what is the basis?
Powers of that.
That's right. So this is going to be zeta. This is going to be zeta squared.
And to the zeta to the power of 5, because it should be linearly independent, or something is wrong.
No, I mean it's all of the zetas, right? In this
but
case.
their sum is 0, so it's not a basis.
Oh, you mean oh.
That's
right. Yes. There's
Sorry, what do we compute now?
We compute a trace matrix, a trace form matrix for this field to compute discriminant. But maybe Petya, you
we
remember
have
something.
formula for discriminant, I think, from the lecture. No?
Okay. Yes, that's true. So what is it?
1 second.
Все-таки, what is the basis of this extension? Stupid question.
I think no. I mean, I mean, I'm pretty sure it's just everything up to. Hold on. Let's see here. What is it? What is it?
So it should contain 6 elements.
Right.
And there is like.
It should contain 6 elements.
Because degree is 6.
That's right. Yeah. So it goes. That's right. So it goes up to 5. Yes.
So it will be just first 5 powers and 1.
Yep.
Yes.
So the discriminant is p to the power 6 multiplied by 6 p or 7p minus 7 minus 1.
So what is it actually? Can you write it down? Let me see here.
Okay. P. Wait. Yes, P. It is. Sorry. It is 7.
Yeah, so it's just 7, right?
Ah, 7 to the power 5. Oh, sorry. 7 to the power 5.
So the square root of the discriminant is 7 to the power of 5 divided by 2, right? And so multiplying it all together, what is the Minkowski bound?
Excuse me, this formula for discriminant works for zeta p only, yes?
I believe, yes, that's right. Yes, so it's, Yes. It also works for powers of p, right? Further down, right? It says.
I mean, we will have problems with 20. So, okay.
We'll get to
Now-
20 in a second. Let's solve this first, yes.
Now we should try alpha.
So now you need to compute the Minkowski bound. So what is the Minkowski bound?
It's the square root of 7 to the power of 5.
Right. So if we plug it into
Multiplied
the calculator.
Yes, I am currently typing it in calculator. And our R2 is again 6, yes, and M is N is 6 2. Oh no, R2 is 3, not 6, because it's half of number of tensions. Yeah. Six. Okay, I've got a number. It's greater than 4, but less than 5.
Let's see here. 6 to the power of 6. Okay, yes, so it's less than 5. So that means that we need to check. So that, yes, that means that any ideal here, any ideal class here contains an ideal of norm 1, 2, 3, or 4, right?
Any ideal, not ideal class, just any ideal. Oh.
What's that?
Excuse me, any ideal contains, not any ideal class.
Any
Or-
ideal contains an element of this of this norm, right?
Yeah, yeah.
Yes. So, right. So now the question is, can it contain?
So we need to prove that if ideal contains, if ideal contains 3, then it's principal, for example. Yeah.
Yeah.
Maybe there is, for example, 1/2 in our ring.
What's that?
Is 1/2 can 1 divided by 2 be an integer here? I think no.
And why not?
Because how to say this? Because there can't be a monic polynomial with root 1/2 by Gauss lemma, maybe even with these coefficients.
Does that really help us?
What I can say is that if we have 1/2, then everything is good. But
If we have 1/2, then everything is fine. Why is that?
because if our ideal contains 2, then it's a whole ring.
That's
For
right.
example. And this will give us that we have no ideals, and it's very strange. No principal ideals.
No, we want
no proper ideals, but we of course have. So it's not what we want to find.
Well, I mean, we know that each ideal contains something of the norm 1, 2, 3, or 4, right? So it could also.
It's not exactly that. It's some integral element of this norm, and for example, 2 has norm 12, so it's wrong.
Mhm.
So we need to look what elements of norm 2, for example, are there. Maybe so how to look at this? Like if you have a basis and norm of like it will be sum of element multiplied by all conjugates.
Yes, so we need to check if 2 in fact can be expressed as a norm of one of these things, right?
For example, yeah.
So can it? Can we write this? That it's
It's norm of something. It's not obvious because if we have some element in this basis, we need to calculate its norm by coordinates and its hard expression.
oh, let's see here.
Sorry, I was trying to put that there is no elements of norm 2, 3, and 4 in this field. Or...
If we can, yes, I mean, for example, if we can show that there are no elements of 2, 3, and 4, that means that, or if, rather, if we can show that any ideal, let's see, what do we want to say?
Excuse me, if we prove that there is no elements of norm 2, 3, and 4, we will get that there is no proper ideals. And
That's
it's
right.
very strange for a ring.
That's right, that's right. So what we want to do is we want to show that if we have an ideal of the norm 2, 3, or 4, this ideal must be principal.
If we have the ideal that contains integral element of norm 2, 3, and 4, we don't say anything about norm of this ideal yet.
Let's see. I mean, from what I read, right? I mean, if you look on Wikipedia, Minkowski's bound. It's at Minkowski's bound. It says every class in the ideal class group contains an integral ideal of norm not exceeding Minkowski's bound. Right.
Okay, we use this for okay. So now we have some ideal at norm 2, for example, which means that
so this ideal
no.
has index like 2 in the ring of integers. So, for example, it contains 2 automatically.
Yeah.
What are you saying? Can you write it down?
There was idea that we have a sublattice on our integer ring, and if it has like rank 2, then it contains number 2. It seems true.
Let's see. Yeah, but okay, so it contains number 2. Then, but can we show that it is in fact principal? So let's see. So what other elements are there of norm 2?
2 has not norm 2, so it's definitely not a generator of our ideal. But we know, yes, that all even elements are our ideal.
So it's kind of finite number of options here. So we know that this ideal is contained within these two guys. And, this factor is z2 to the 6, I suppose. So there's like 63 possibilities for I in total. In principle, we could check all of them.
I don't like that idea. Let's see.
Simplify the task.
Let's see here. See. This is see.
So maybe I can say that this guy is actually a ring, and we can write, and it's probably isomorphic as a ring to this z to the 6, and so we can write the explicit basis, and we know that I modulo to O is a subring of this guy. There's not too many options then, like 6 options.
Well, yeah, okay.
So then we need explicit basis for this guy.
Explicit basis for what? For this?
I mean, like tell which elements of O like, are the basis of this ring. So I think I claim that there are some you can find some 6 elements in O such that the pairwise products are divisible by 2. Distribution belongs to 2. And I guess they are linearly independent mod 2. That's what I'm trying to say. So that's if we write them explicitly, then And if it's actually true, then I is one of 6 options here. You take 5 x's out of them and generate something. And you check that all 6 of these ideals are principal.
Okay. I'm just thinking. I mean, can we come up with any example of an ideal of norm 2, for example? Mm. Let's see. Let's see. Mhm. Here. Mhm. Yeah, so let's see. First of all, yes. So yes, okay, yes. So let's look at at 2 and at 3, right? So how does 2 split in this extension?
You mean prime ideal 2?
Yes, prime ideal in Z. So we look at the prime ideals in Z.
So we calculated its discriminant and its comprime to 2. And splitting is about field discriminant.
No, I mean, like, does this ideal is it still a prime ideal here?
We should look if it is a residual modulo 7 to 5.
You mean like
Quadratic residue.
So 2 is residual modulo 7. That's and so it is prime modulo 2 is prime.
2 is prime, okay. And is 3 prime?
Three is not prime.
So how does 3 split? Can we come up with an explicit way for it to split? Let's see. How do we do that? Okay, so we need to take what? We need to take the discriminant was 7 to the 5th, right?
I'm sorry, 2 splits, but 3 does not split. It was my mistake.
Well, let's see here. Yeah, okay, you're saying 2 splits and 3 does not split. Okay. And what does 2 split into?
How do you check so quickly that something splits or not? You have to verify that some polynomial is reducible mod 2 and 3, right?
Katia, how did you check that?
So we had a theorem that number. Oh, sorry. Maybe this was a theorem about a particular case when we have Q with square root of D, but I'm not sure. There was a theorem that it is ramified if it divides the discriminant. It is a prime if it is if the discriminant is not a square modulo P, and it splits if it is a square. Oh, so we should look at 7 to 5 and look if it is a square modulo 2 and 3. Yes. Sorry.
Yes.
Does that apply? Does that apply to all? Does that apply to all extensions or just to quadratic ones? That theorem.
So I think we proved it for quadratic ones. So maybe it is not true in this case.
So what is the quadratic extension in here? What will be the quadratic extension in here? The corresponding quadratic extension. The corresponding quadratic extension would be z.
We calculated it. Yes.
Yeah. Well, you can say it's that it's that. Let's see, square root of minus or plus 7. I think it's minus, right?
What is this? It's some quadratic extension inside our extension. Or the...
Yes. You know that every, well, I mean, we can actually show, right, that yes, we can actually show that any for any prime zeta extension of Q by zeta sub that prime contains a quadratic extension, and here it depends on plus or minus in front of 7. That depends on whether you know, it's mod whether it's 3 mod 4 or 1 mod 4. Yeah, we can actually show that.
It's strange enough because I remember that cosine of P over 7 is not expressed in radicals.
What's that?
But okay. So you mean that like zeta 7 is some quadratic thing, is some number which coordinates can be expressed using this square root of -7?
No, I'm not saying that. I'm saying that square root of -7 is contained.
Okay.
Yes, the extension by the square root of -7 is contained in inside of that extension. So we need to check that in whether in this 2 and 3 split.
So if split even in this, then split out here.
Well, let's see. Yes. So if it splits in this, then we fail, right? I think. Well, I mean, okay, it depends. It depends. So let's see here.
So obviously, 2 is 9 minus 7. So it is 3 minus square root of -7 and multiply by 3 plus.
And what is the norm? Yes, and what is the norm of this inside of the bigger ring? Let's see. 3 plus. So that gives us 2. Oh, I guess, sorry, it's actually So this is just so this splits. Let's see. Two splits. What is the norm? So let's see here. And what is the norm of this? The norm of this is bigger, should be very large, right? The norm of each of these principal ideals.
It should be 8.
8? Yes, right. Yes, so that should be 8. And this is 8. So what can we say here? We can say, right. We can say, let's see. Yes, that's right, it's 8. So what can we say in this case? We can say that any ideal, that's right, we can say that any ideal class yes, any ideal class. Okay, and what about 3? What can we say about 3? Can we write down 3 in this? Let's see.
Well, 3 is a prime.
7 minus 4.
No?
Is different. 7 minus 4.
Yeah. So we can. That's right. That's right. So we can write it down as yeah, square root of -7.
-7 of 7. You write just 7 in
Yeah.
position for 2.
But yeah, okay, yes.
And do we contain it? Is it legal?
Square root of 7.
7 minus 2 minus square root of 7 plus 2. But is this square root of 7 legal?
Yes, it's square root of 7 legal. It should be, hold on, let me double check. I think square root of -7 is legal. But is square root of 7 legal? Tell you in a second.
They can't be both legal.
Right. They cannot be both legal, obviously. Yes, it's -1 to p minus, so it's 6. Divided by 2, so it's 3. No, they cannot. They're not both legal. Yes, so it's only -7 that is legal. So can we show? Yes. Can we split?
And how to remember this? What
Yeah,
it depends on the modulo 4 or something like this.
That's right. It depends on it's -1. It's basically p times -1 p minus 1 over 2. I think we would have to, we have that in this seminar as well. Eventually, we have that as a problem in this seminar. But anyhow, yeah, so this is the one, this is the, yes, this is the square root that always lies in here. But anyhow, yes, can we show that, what can we say about square root of -7? Can we express 2 and 3 using that?
I think no.
No, I don't think, yeah, I don't think that's possible.
Maybe we could just write an equations for a plus b square roots of -7 multiplied by this.
Yeah, so we have a squared plus 7b squared is equal to 2.
Excuse me, why is this? Because these two splitting fields should be conjugate, yeah? If it splits, then it splits to product of two conjugate fields. And this is obviously can't be true.
Right. So, in other words, yes, we can show that, yes, in other words, we can show that this doesn't split and this doesn't split, right? That means
Does it split in a sub-extension?
in the sub-extension, yes. Doesn't split in the sub-extension.
Hold on, but we still have like 3 plus square root of -7 times this guy is 16. So
what?
well,
That doesn't help us.
doesn't.
No. Because we want to show that 2 and 3 split, right? And we just showed that 2 and 3 don't split.
Well, then I don't understand why 2 doesn't split. It's if you consider the polynomial for zeta 7 mod 2, it's reducible because the minimal extension of f2 in which contains 7th root of 1 is f8. Right. So minimum polynomial for zeta 7 is a product of two guys mod 2. Of two polynomials of decreased root. This implies that 2 splits in Q at zeta 7, right?
Let's see. Hold on. How does it imply zeta 7 in F8? Okay. Let's see.
Well, we even had a theorem today that in order to figure out how this guy splits mod p, you have to look at the minimal d such that 2 to the d is 1 mod 7.
Is 1, 7, yes.
Yeah.
Right. So 2 does split. So how does it split? Okay.
But as we seen, there can be product of two numbers equal to 2 or not.
Mm-hmm.
You can write here 1 instead of 3, then you get
We get 8.
8. And I suppose that you can divide this by 2. Probably this is an integral element.
Is this still I guess, yeah, I guess that would still be an integral element, right?
Yeah.
Mm-hmm. Mm-hmm. Mm-hmm.
It's probably the way.
Okay. So this splits. So now we want to show, all right, what do we want to show? We want to show that yes, and does 3 split?
No.
3 does not split, right? So 3 is okay, but 2 splits. So now we want to show that if we have that
Why? What we say about 3?
I'm sorry?
Why 3 don't split on the?
Because the minimal
Because of the
extension.
theorem, yeah. Mm-hmm. Because of the
So-
theorem discussed today. Mm-hmm.
You have to take f3 to the 6
Mm-hmm.
in order to get the 7
Mm-hmm. Mm-hmm.
be contained there.
Mm-hmm. Yep. So now we want to show that, let's see, so we have, so that means what? That means that if we take the ideal, if you take the ideal generated by this inside of here, then we should get Z mod 2. Yes. Okay, so we know, yeah, we know that O, we know that O divided by this. Right.
But isn't the norm of this guy is too large?
Yes, the norm of this guy is too large in the end. Yes, so I think that's, let's see. So 2 splits means what? Yeah, because shouldn't we get that the norm of this guy ends up being 8, right?
Yeah.
So that means that O mod this guy is going to be what? Z over 8? Right?
Oh, mod this guy is f8.
F8, yeah. It's F8. Mm-hmm. Yes, so it's F8. Uh-huh. It's kind of strange. Let's see. So it ends up being F8. Oh, I think, can't we just say something simpler, I guess? You could, yeah, well, I guess that's enough. Yes, I guess that's enough because we can say, yes, that it ends up being 8. So if we did have, yes, if we did have an ideal of, if we did have an ideal of order 2, right? Then I mean, of norm 2. Well, we can't have that. We cannot have an ideal of norm 2, basically, right?
Yeah.
Why?
Because if you have an ideal of norm 2, then it's contained between 2O and O. But if it contains 2O, then there are only 4 possibilities for I. I could be like 2O, O, and these two guys.
So these guys are prime in our zeta 7
Yep.
or zeta 7 ring. We proved it. Okay.
Yes. Yes. So right. Yes, it would be one of these 4 possibilities, and that's impossible because the norms don't match up. So then 3, we know that 3 doesn't split, so we shouldn't care about 3, right? Because 3 will always be principal. Because it was principal in Z, and hence it will be principal here as well.
So there is no ideals of norm 3 because any of it will lie over 3. Or what they're saying.
No. I'm saying that the only ideal that lies over 3 is 3.
Yes, and any ideal of norm 3. Okay.
So if there is an ideal of that norm, then it must be yes. So that means that the only ideal that lies over 3 is 3, and it's principal, right? So it would be trivial in the ideal class group. Well, 4 we can argue analogously to 2. So we cannot have that one either, right? So that means that since any ideal class must contain an ideal of one of these norms, right? And we know that for 2 it cannot happen because of this, and for 3 it cannot happen because 3 doesn't split. We know that. We know that for 3 it can happen, but what's it called? For 3 it can happen, but the ideal will be principal. So that means that the ideal class group is trivial, in fact. Right? Do we understand this? Right? Does everybody understand?
So.
Okay, so let's do. All right, let's do Z20. Oh yes, Z20. So what is the discriminant of this one? What is the Minkowski bound of this one?
So we need to calculate the discriminant.
So what is the discriminant in this case? Let's see. The formula that he gave us, it's only good for powers. All right. Only good for powers of primes. Let's see.
Not maybe we can compute the polynomial explicitly. It's on the degree 8, I think.
That's right. Yes. Oh, we actually have it, right? Yeah. We have it in the lecture. x8 minus x6 plus x4 or 4 minus x squared plus 1. And what is the discriminant of this? And what is the discriminant of this? Let's see, I guess we can just look it up.
So we need to find greatest common divisor with derivative, or it's not. So this
Yeah, we could do that. Or I wonder.
we don't want to find roots, I think.
Right. Well, I mean, or we could just look it up. So, well, looks like the discriminant of this polynomial is 4 million. So what is the formula for the discriminant? The relationship between the discriminant of the field and the discriminant of the polynomial?
They're equal.
Oh, in this case, they are equal.
In this case, they're equal. Jesus.
In case when extension is generated by one element. Yeah.
Okay, so in this case, it's the discriminant is 4 million. So if we plug that into our Minkowski bound, what do we get?
Excuse me, how did you get this 4 millions?
I don't know. I mean, I just looked it up.
You mean like in Wolfram?
Yes.
It can do this. I have, by the way, a question. Like, if we count greatest common divisor with derivative, then we will get a polynomial. And what should we do with it to get a number which is discriminant?
Well, I mean, we have a formula, right? We have a formula that we discussed in class, which basically ends up being you just plug in, you just multiply together differences of what's it called, the roots of unity, right? And that was the formula for the discriminant.
You mean just roots of this polynomial?
Yeah. Well, yeah. Roots of unity. Yeah. Right.
But I am asking if this discriminant related to polynomial discriminant, which is greatest common divisor of polynomial and derivative.
Same thing.
No, because polynomial derivative is a polynomial and we have a number. And it can be the same thing.
Well, we need to take this what's it called, this greatest common divisor, and then we need to plug in the root of unity, I think.
Any of it,
Yeah.
root of unity.
But anyhow, yes. So if you take this 4 million now and we plug it into Minkowski bound, what do we get?
I think it's something between 12 and 13.
Between 12 and 13?
Yeah.
Okay. So, all right. So let's say it's 13, right? Yeah. So okay. So we need to go up to 12. So we need to check 1, 2, 3, 4, 5, 6, 7, 8, 9, 12. 8, 9, 10, 11, 12. Right. And what do we do? Etc. What is this noise? Hold on. Okay, good. All right. Yes. So we need to check. We need to check how this split. Well, I think we could also check instead. Couldn't we just check instead whether any of these polynomials, couldn't we just check whether any of these numbers is just a power of 8, right? And we can say that there are no powers of 8 here. Wouldn't that be enough? Because, let's see.
So like, there is no completely splitting numbers here.
Oh yeah, that's true. So okay, so I guess we need to go through this whole process again, right? So we can look at we can look at the quadratic subfields of this. So what are the quadratic subfields of this? They're the ones that correspond to square root divisors of this, right? So that's 5 square free dividers of this. So that's 5 and 10, right? And yeah, so that means, and do we have plus n minus? Let's see, what was it? It's z over 20. Right. Oops. The multiplicative group of z over 20. And what is how many subgroups of index 2 do we have here? Anyone?
Quadratic subgroup, index 2 subgroups in.
Yeah, index 2 subgroups and z mod 20z. Star.
So we need to rewrite like what that group is. It contains like 5 multiplied by so it has 8 elements again, and is the like element of order 4. Yes, because if we like take 3, then 3 to the power of 4 is 1.
3 to the power of 4 is 1. Let's see. What is it? 3 to the power.
So we need to check that there is no
that's right.
elements of
Power of order 8.
of order 8.
And are there any elements of order 8?
No.
No. Okay, good. All right. So we just take z mod 2 times z mod 4. All right. Yes. So how many subgroups of index 2 does this have? Anyone?
This subgroup can either contain whole that for either half of it, so 2. Like, no, it's a product.
Yeah, it's probably.
We are seeing an image on projection to second coordinate. Yeah, and if it's a whole thing, then
Well, let's see.
yeah, consider all second coordinates of our elements.
Uh-huh.
If it's not whole Z4, then it's Z2 inside, and we have only one such subgroup.
Mm-hmm. So altogether 4, right? We have 4 subgroups of index 2.
No.
No, hold on.
Why 4?
Let's
I
see.
think that we have 3.
3, right. Okay. Mhm. Yes, 3. Yes, so let's see. And we have 5 or 10 to choose from. 5 and 10 to choose from. Oh, okay, sorry. Yes, we also have 2, right? We have 2, 5, or 10 to choose from.
What is these numbers?
The divisors of 20. Mhm.
Square free divisors for quadratic subfields. Okay.
Yeah, square free divisors. Okay, so there's 2, 5, and 10. I guess that's it, right? Because yeah, I guess this is all we can have. Or are there 6 or 3? Only 3, right?
We can check it, but I think that yes, because again, if there is like all Z4 in second coordinates, then it has a generator, and if we consider pre-image of this generator, then it have a 1 or not have 1 in
Right.
left coordinate.
See.
So it's 3 subgroups, and there is a -1 inside, of course, square root of -1. So, and
Right.
square root of 2. So it's 2 minus 2 and
Yeah, let's
-1.
see.
So there is no square root of 5, for example.
There's no square root of 5?
I think yes. No, as you say, even in U of zeta 5, there is plus or minus square root of 5, and
That's right, yes.
so it should be.
It should be here too. Well, let me check how many subgroups does this have. So let's see. It's got, yeah. So it's either 3 or 1 here. Okay, and then here we can take. And here it has to be 0. That's 2. We also have 1 here. We have 1 here. Let's see. 2. Let's have 1 here. And that will give us 1, 3, 1. But they really generate. Generate the same subgroup. let's see explicitly what do we have. We have 0. We have a subgroup generated by 0, 1. We have a subgroup, and we have a subgroup generated by 1, 1. And what's the third one you were saying? Oh, I guess. And what is this? Oh, and I guess we also have a subgroup. What other subgroups do we have? It seems like we only have
Non-cyclic, not non-cyclic. It's Z2
yes,
multiplied by Z2.
Z2 multiplied by Z2, yes. Yeah, Z2 multiplied by Z2. And oops. Z2 multiplied by Z2. And there's only one like that?
Because in Z4, that is only one element of order 2.
Right. Okay. All right. So, yes.
So there should be only 3 quadratic subfields, but it's strange.
It's strange because wouldn't we have, we should have, what's it called, I also in here, right?
Yes, it's this Z to the power of 5.
Mm-hmm. Yes. Huh, could it be? Let's see.
Maybe it depends on modular 4 that in ring like of zeta7 we have square root of 7 and now we have not
Square root of -7, right?
-7 and now we have no 5 and no -5. I don't know this fact, so you are using it and
Right.
saying that it's always true or not.
Let's see. Yeah, so it should have -5, right? No, 5. Yes, it should have. No, yes, it should have 5. So it should have square root of 5. We should have square root of 2. Hmm. 5 square root of 2.
Do they need subgroups of index 2 but not of 2 elements? Because there is a good number of 2 elements subgroup.
No, we need of index 2, right? By the Galois theory.
Maybe we calculated group wrong.
Yeah, maybe we did. Let's see. 1, 1, 3. Oops, 1 second.